Okay. I guess I will go ahead and get started. My name is John Muno. I work for Arthur J. Gallagher. We're an insurance broker in the United States, and we're actually all over the world. But I was invited to give a presentation on battery energy storage systems, their design, the risks, and what happens when we try to integrate them into the grid. I have been an energy risk engineer for over 40 years. I've worked for power companies, for oil and gas companies, onshore, offshore. And about 15 years ago, I came to work for an insurance broker, and I've continued to help clients manage risks. And well, I've seen everything from thermal power plants all the way up into the now the renewables. And what I've done lately is started to learn a lot myself about battery energy storage systems, and I'm going to share some of what I've been learning with you guys. So I'm not sure how the format goes, but I will go ahead and get into it. I'll share my slides. Hopefully everybody will be able to see as I share. And
hello, everyone. Thank you, Mr. John.
hello.
Yeah, this is Muhammad from GCC CIGRE. Welcome to this webinar, and we welcome all these attendees, and hope you will enjoy this interesting subject now. Now, the stage is yours. Can proceed, Mr. John.
Okay, thank you very much. So at the bottom there, you see my name and title and my email if you want to reach out to me directly. I also have a YouTube channel as a hobby on the side. It's not part of anything that Gallagher sponsors or endorses, but for a few years now, I've been recording videos that help aspiring young risk engineers learn to be better risk engineers, and for chemical and mechanical engineers, so that they can maybe, if they're interested in risk engineering, they can learn something from all of my experience. I also put my LinkedIn address there. I'm very active on LinkedIn. That's somewhere where I can post articles, I can get feedback, and it's been very interesting as some of my articles have gotten more popular. Vendors and contractors have reached out to me to explain their products. So I've taken the opportunity to record interviews or podcasts of those product descriptions. So when someone's developing a new technique for fighting fires involving dry ice, I send them a list of questions, and then I go through all the questions, and we put together a pretty good interview. So with that, let's get started in today's subject, the batteries. And what we're going to talk about first are the configurations and the chemistries, lithium iron phosphate, nickel manganese cobalt. Then we'll talk about the failure modes, the different causes of the problems that we have in risk management. We'll talk about current fire spacing guidelines. I wrote a paper about this that got widely popular on LinkedIn. And there are some differences in the way the different insurance companies approach fire spacing guidelines. So we'll talk about that a little bit. And we'll talk about real world insights from full scale UL 9540A and CSA TS-800 fire testing. It's interesting that these tests are required in some cases, so we get a lot of information when we do a real full-scale test. I don't think I've seen this in the past. Even in steam turbines, we rarely could do a full-scale test, but now we're doing them with battery energy storage systems. And I have a set of tools that I want to introduce that's been around for decades, but NUREG-1805 has fire dynamics tools, and we can use those to calculate radiant heat and plume modeling if we have already got a battery system installed and a question comes up, is it safe or not? We'll talk about deflagration venting design considerations and Finally, we'll talk about the most important subject to the utilities, and that's the integration of the impacts on the T&D infrastructure, such as reverse power flow, resonance, fast frequency response. Now, let's get into it. The core configurations and chemistries. We hear of lithium iron phosphate, LFP, and nickel manganese cobalt. There's many, many other configurations, and today we're just going to talk about these two because this is what we see most installed right now. And starting with lithium iron phosphate, it's a lower energy density, so it won't have as much energy in a particular module as the same size nickel magnesium cobalt would. However, they are superior in thermal stability. They have a lower thermal runaway risk. And it's not zero, but it's lower than with NMC. The cycle time is longer, so they can be used for a longer period of time. They're safer for indoor or urban siting. They're less reactive. And if safety is the priority, then these are preferred, lithium iron phosphate. Next, we have nickel magnesium manganese, nickel manganese cobalt oxide. They have a higher energy density, so they can hold more energy per volume of battery, and they're better for compact installations. They have greater thermal sensitivity. That means that they have a narrower, safe operating window. You have to keep them cool while you're operating them to make sure that they don't get too cold or get too hot. They're good for space-constrained mobile applications. This presentation, by the way, is very text-heavy. I hope I don't kill you with PowerPoint, but I figured that it may be challenging to keep up with my accent and the speed of my presentation because I'm going to cover a lot. So if I give you all this text, it'll be easier for you to follow along. So how do we configure BESS systems? We've seen them containerized, we've seen them in racks and skid mounted. And the containerized systems hold the racks of the modules. And within that container, we'll see a HVAC system, a battery management system, BMS, see some fire detection, and they're basically standardized, and we'll see it both for LFP and NMC deployments. And with rack design, we may see those systems being installed in either purpose-built buildings, or I've seen with utilities and power companies that are decommissioning fossil burning power plants. I've seen the turbine decks just become full of battery energy storage systems for use on the grid. And then skid mounted systems are a little smaller, but it's pre-assembled. It's got everything in one package. So what can go wrong? Thermal runaway. We hear thermal runaway, and it can be triggered by overcharging it, physical damage, or internal defects. It's self-propagating, it's exothermic, it gives off heat when it starts, and it can lead to the full container fire. And it's a higher risk with nickel, but lithium phosphate, the iron phosphate are still, it's possible. It's not immune to them. I know in the beginning we used to say, oh, lithium iron phosphate can't catch on fire, but it can, and it can off gas. And in fact, some of the concerns with lithium iron phosphate are that it can generate a larger plume or vapor cloud that has to be managed or addressed. So there are trade-offs, but all of them require multi-layered controls, battery management systems, thermal barriers between the cells or the modules, thermal barriers within the containers, and then the spacing. UL 954A tested enclosures, fire suppression, ventilation, and gas detection. Some other things that we're seeing now, and I'll mention this on, when I said earlier that I've been interviewing entrepreneurs and developers of new techniques and new equipment. A few companies that do battery monitoring have reached out to me. So I see that one company, Validica, they will take just your raw SCADA data, nothing new needs to be installed at your facility, and they will analyze it on their end and as opposed to these systems that depend on gas detection, that's telling you that a problem's already occurred, that there's already a active thermal runaway occurring by the time you're detecting gas. And the manufacturers of the gas detection systems talk in minutes, how many minutes after the thermal runaway starts that we can detect the gas. The monitoring people will tell you that they can predict thermal runaway a few days or a few weeks before it happens. That's the Validic approach, where they don't use AI, but they just take all your raw data and they analyze it. Then there's another company called Electra Vehicles that has developed a program where they install the equipment to do AI analysis of your battery management system first. Then they transfer the data to the cloud and they monitor it remotely. So both these companies provide a third-party monitoring system that will keep track of your batteries before they experience thermal runaway. So on my YouTube and on LinkedIn, I've interviewed these folks, and there's links to the videos, so you can learn more about monitoring the batteries remotely. And the insurance companies really appreciate that, where when there is remote monitoring, they feel like the operators have their hands full trying to juggle the price of power and the age of the batteries and the condition of the batteries. And just trying to do it all at once can be overwhelming. Whereas, all the remote monitoring folks are doing is trying to make sure that you don't have a thermal runaway or some other event imbalance that could lead to a failure. So what are the causes? Overcharging, high temperatures, internal shorts, physical damage. What can happen? Fire, explosion, release of fumes, battery damage. And again, it's self-heating. There's a release of gas and it spreads to other cells. I'll mention that I was at a conference a few months ago and Tesla was there. And Tesla announced that they use a sparker system where they install about 10 or 11 sparkers, igniters in the battery containers. And the purpose of these sparkers is to ignite the combustible fumes, the gases, before they reach a point which could cause an explosion that would damage the container. So by having this continuous presence of sparks, they eliminate the potential for an explosion. It's a very interesting approach. With that, they also say they don't need a fire suppression system because they're not going to have a fire. They may have thermal runaway, but they're going to deal with the gases before they become too great and could cause a explosion that destroys the modules. What else can go wrong? We can have HVAC loss or degradation. And what happens there is that our batteries can overheat. And this is just something that we can monitor before we get into the batteries going into thermal runaway. So it helps if our monitoring includes the HVAC. And if we don't have good monitoring of the HVAC, then we may just be relying on the BMS, and so we're just waiting for the failure to happen. And little things, I can't tell you how many sites that I've been to, and I've seen either dirty air filters or fans, the spare fans just laying on the floor, the ground, where you can tell they've been replaced. The maintenance, obviously, they go out and find failed fans. Well, guess what causes fans to fail? They fail when the air filters get clogged. And why would air filters get clogged? Especially if you're following the manufacturer's recommended every 6 months, replace the air filters. I've seen it where the conditions on site are so dusty that the filters need to be replaced more often than what the manufacturer recommends as an average. You have to remember that your site-specific conditions are going to dictate your risk, and that all the manufacturers can do is give you a general idea of what they see across their entire fleet. So you have to take your own experience into account when you're dealing with HVAC systems, and make sure that if you start to see fan failures, start changing your air filters more often. All right, what else can go wrong? DC arc faults. And what we see here, loose connections, especially the MC4 connectors and mismatch connectors is a problem in solar farms. But anywhere in the battery system, if we have loose connections, damaged installations, we're going to start to see DC arc faults. And these can lead to fires, they can lead to equipment damage and personnel hazard. We need to have arc detection and interruption. So within milliseconds, we need to either in the BMS or in the DC combiner logic, we have to be able to shut down the battery so that we don't continue to cause an arc that just gets worse. What else? And this is when we get into a little bit of the impact on the grid, harmonic injection into the grid. So inverters switching creates high frequency harmonics. And what that'll do out on the grid is that can overload or overheat transformers. It can cause misoperation of relays. It can cause nuisance tripping in nearby substations or loads. And this risk increases if you have poor inverter grounding or filtering, high inverter saturation in feeder circuits. And something else that goes along with this is data centers. And this talk is not about data centers, but they can do the same thing. They switch their loads on and off very rapidly when they go from learning mode to inference mode. And what that is when we have a data center, we have a big computer, and at first we're trying to teach it what we need for it to be artificial intelligence. And just as a simple example, imagine scanning an entire encyclopedia or dictionary and then uploading that into a computer. Well, that's the learning phase of this process. Then when we start asking it questions, it goes into that learning memory and it looks for words that are probably the right word. So it uses probability. And this is the original way we deployed AI. But it goes back and forth between learning and trying to answer the questions very rapidly. So data centers can also cause some of these harmonics and problems on the grid. And we really need to be able to separate the two. If you run a T&D operation, it's very important that if you're having any equipment failures on your T&D system, that you investigate them to determine, are they being caused by systems like batteries, solar, or wind, distributed energy sources, or are they being caused by data centers? So a lot of times the data centers can install battery modules to clean up the power. In fact, here in the States where Elon had a huge center being built, he didn't have time to wait for the solar and wind equipment to be adequate to run his data center. So he was installing simple cycle gas turbines. And in order to smooth out the power from these simple cycle gas turbines, he ran the power through megapack battery energy storage systems to clean up the power. So be aware that data centers are also out there and they can also cause harmonic injections into the grid. All right, now let's talk about current fire spacing guidelines. I wrote a paper on this that got a lot of recognition on LinkedIn. So FM Global is one of the companies that looks at batteries. AEGIS, that's the Associated Electric Gas Insurance Services, and AIG. They all are large global insurance companies, and they have different guidelines. And it's interesting that they're going to have different guidelines. But FM Global prefers 50 feet unless you've got some kind of mitigation, such as having passed a full-scale 9540A test without external flame propagation, if you have approved thermal barriers, and if you have gas detection, BMS, and fire suppression. Firewalls must extend 5 feet or 1.5 meters above the and beyond container edges. So FM's got their conditions in order to lower the spacing, but they're not as restrictive as AEGIS would be. This is another example. So AEGIS, they basically work with their members. They're a mutual company as well. They don't write insurance. Well, they do write it for non-members, but they are trying to back out of that. especially for battery energy storage systems. They're trying to support their membership that already buy insurance for casualty in the energy space, such as electrocutions, third-party, fatalities, anything that has to do with protecting the public. That's what AEGIS's main focus is. When the utilities and their members started to get into battery energy storage, they joined along, but they're pretty steadfast in 25 feet. They want this separation. They will accept mitigated spacing or closer spacing. I had a facility that was about 10 foot of spacing, and we were able to talk Aegis into accepting that spacing. Now, that wasn't a typical BESS. What it was a black start BESS. So it was there to help restart gas turbines that were there, believe it or not, to back up the wind out in Palm Springs, California. It's an 800 megawatt plant that has 8 LMS 100 GE gas turbines, simple cycle gas turbines. They can start up in 10 minutes, but that's not quick enough for the grid. So we installed a BES system that will help support the grid, but mainly to get these gas turbines all up and running if there's a grid outage. But AEGIS would like to see actual testing on your configuration and your equipment before they're going to accept less than 25 feet. Just be aware of that if you ever get to working with AEGIS. AIG, they're much more reasonable. They would like 10 feet of separation. 10 feet is what even the manufacturers who have tested to 8 feet suggest. So Wärtsilä has done some full-scale testing, and their testing suggested that at 8 feet, there's not a huge risk of propagation from container to container. But they say that they recognize that you need about 10 feet just for maintenance activities. So with that, they're about the most reasonable, and 10 feet seems to be what all the following markets like to see as well. So what can go wrong with your spacing reduction? What can drive it towards not being accepted? Well, nickel, manganese, cobalt systems, that don't have a good 9540A test, or if you've got shared HVAC or cable trenching that can, cause the fire to go from, one container to another. And then lack of gas detection or alarm interlocks. So what is 9540A and CSA TS-800 fire testing? Well, it's full-scale testing, and it's there to determine whether thermal runaway propagates between cells, modules, racks, and containers. And it's there to quantify the gas composition, the heat release rate, and the flame spread. And believe it or not, there's not a pass-fail criteria. What it does is it just documents what happens when a cell is put into thermal runaway. Does it propagate to the next cell? Will it propagate through a module to adjacent modules? Will it propagate across racks or beyond containers? So it's there to just give us information. 9540A is not a pass-fail test. But we can use it to determine if we need other risk mitigation, such as spacing, suppression, or gas management strategies. Again, the gas management can be ventilation, it can be active, it can be passive, or it can be the sparkers, as Tesla uses. All right. 9540A is North American based. It's a 4-tier approach. They first start the cell in thermal runaway, and they'll do that with heater rods or nail penetrations, sometimes torches. And they want to see, does it go to the module? And if it goes to the module, will it go to the next module? And so on. So it goes all the way up to, will it spread from container? So be careful. We'll talk about some of the things to watch out for when you have these test results. And the typical findings are that lithium iron phosphate systems often self-extinguish at the module level with little external flame, whereas nickel, manganese, cobalt systems are more likely to show vertical flame jets and lateral fire spread, or vented gas ignition. The gas that comes out is carbon monoxide, hydrogen fluoride, and these are flammable. Okay, a lot of people don't think of carbon monoxide as a flammable or combustible gas, but in the right concentrations, it certainly is. And ventilation is critical so that we don't build up an explosive concentration, or we can use the sparkers like Tesla does. Container level tests are frequently show delayed ignition. See, that's always a problem. When you don't have immediate ignition of these gases, you build up an explosion potential. So we have to make sure that we don't have a technology that can do that. So when you fail the test, sometimes you are going to have wider spacing, requirements for active suppression, gas detection, thermal barriers, potentially remote monitoring. And some manufacturers offer remote monitoring. Like I said earlier, there are third parties that will perform remote monitoring. And if you use a third party, you're not tied to one manufacturer. So if you install a system at one site and the OEM, that's who's doing your monitoring, then you go and you look at a new site that uses a different technology, you're going to have to find another provider. So there's some advantages to just out of the gate starting with third party providers, and the insurance companies kind of like them better. There's no real data on that, but any third party monitoring is better than none. But having a company that's not tied to the active technology gives it a little bit more credibility. So look into those third party companies. And the CSA is Canadian based. It focuses on energy systems as complete assemblies, not just cell behavior. And there's a big emphasis on fire service interface. We haven't talked much yet, but how does a fire service deal with a battery storage fire? Best thing is, and this is from listening to fire chiefs that have responded to many of these, is to not actively try to extinguish the battery fire, but to basically monitor the flume, to protect exposures, to try can protect the spread of the fire from one module to the other. They're not trying to extinguish this fire. They've already realized that that's probably not going to happen. It's going to burn itself out when it's out of fuel. When we do the full scale fire tests, some of these tests last 10 or 12 hours. So just imagine trying to have 10 or 12 hours of firefighting going on and all the logistics needed for that. You're still there for 10 or 12 hours as one of the modules burns, but you're not actively trying to put it out where you could become injured. All right. So the key takeaways for engineers and underwriters is that not all 9540A tests are equal. The results must match the actual BESS design. And you can't just use, the fact that this manufacturer's Model A was tested. Now we're going to install Model B or C or D, and you have to test exactly what you're installing. And the propagation depends heavily on the spacing, the vent direction. So we've seen vent designs where the side of a module has a vent installed, or the top of the module has a vent installed. And when it's on top, that prevents the exhaust gas or heat from impinging on a nearby module. But it's also subject to snow loads. So you have to be careful that if you are in a snow heavy region, that you wouldn't want to put your vent on top. If you are not, then it's okay to put it on top. Then you prevent the vented gases and vented explosion from impacting another module. And we got to look at the HVAC airflow and the path and how we cut it off, because that will influence these fire tests as well. So the data helps us reduce the fire spacing from as much as 50 feet down to 3 feet if you can work in that space. And it exempts us sometimes from full suppression systems if we have a good test. So the data from these tests is very important for helping us finish our design on our system. And that's why we can't wait till we've already finished the design and then go get a test. So what you watch out for in risk reports are claims, just blanket claims that it's UL 9540A tested. What's that mean? Well, be careful about what that means. They've got to provide the data from the unit and installation level testing. And just because it says or if it says 9540 certified, that doesn't mean that it's passed propagation fire tests all the way to at the installation container level. And nickel metal uh, cobalt systems with rack levels still require container level validation. So just because it passed at the cell or module level doesn't mean that it's really a safe system. All right, so now here's some tools that I want to introduce that can be used to calculate if there are any fire protection engineers in the audience. What I found is that NUREG 1805, it's been around for decades. It was developed for the nuclear industry. It's developed by the nuclear NRC, Nuclear Regulatory Commission in the United States. And what it is a suite of simplified fire models. They're all Excel spreadsheets. And you basically type in your information and it'll give you an answer. It's designed for quick, conservative analysis. It's not what will replace a full CFD or computerized fluid dynamics model. But if you just want a quick idea of will my battery design spacing work, you can input a estimated heat flux from a fire and determine at a certain distance will it catch the next module on fire. And they're free. The tools are on the NRC's website, and if you just Google that Fire Dynamics Tools NUREG 1805, you'll be able to find them. And some of the key tools they have the radiant heat tool, and this is good. Like I said, it will help you determine what the radiant flux is at your target. This is good for fire protection engineers if you've got generator step-up transformers as well, and you're trying to figure out, well, you've got two transformers, a station service transformer and a generator step-up, and you want to know if I had a fire on my station service or my auxiliary transformer, will there be enough heat to cause damage to the GSU if I don't have a firewall? This tool is very helpful in determining, especially for existing installations, will I need a firewall or not? Then the plume tool helps predict the movement of the hot gas plumes. The jet tool will help us, model a container jet and then give us the heat flux again so that we can determine whether adjacent equipment or structural components are going to be exposed. And then the vent tool gives us an idea of the size of our vents and, just the gas release timing for enclosed spaces. So it's helpful. These tools are free, and I'm just pointing them out so that if you'd like to take a opportunity to use them, you certainly can help answer some questions. But just be aware that they're conservative by design. They may overpredict the heat flux or the gas buildup. They're not dynamic. They assume a steady state fire. So, when we do a full scale battery fire, it starts small. It starts in one cell and they grow. So that should be taken into consideration. And if you can do a full scale test, try to validate these models against the full scale tests. But for screening, it's ideal. It's good for justification of site specific mitigations like spacing waivers, like trying to convince the insurance company that your spacing is adequate without doing a test. So this is some of the limitations and considerations. Now we're going to get into the BESS integration impacts on the grid. What is it that the BESS systems do to utilities and T&D systems? Let's talk about reverse power, resonance, and harmonics. So reverse power can happen when the battery system discharges into the grid, pushing the power upstream towards substations or generating sources. Most of the equipment, the legacy equipment, was designed for electricity just in one flow, one direction. So we can impact relay coordination. We can have voltage rises at weak nodes, And this is something that we want to learn about, the difference between, was it a battery system or was it a distributed energy source such as solar, wind? Was it a data center? So a data center is typically not going to be injecting power. They're going to be receiving power. They're going to be a load, but they're going to draw that load back and forth, up and down. And so they're going to cause instability in the voltage on the system. Whereas these battery systems, they're going to put power into the system, not just voltage. And, when we backfeed a transformer, we can accidentally de-energize lines. So that can cause outages. And if we have these and we wonder what's causing it, we need to look at what's recently been installed on the system. Have there been BESS projects installed lately? Have there been other data centers or other loads that would cause us this issue? So we address it by revising our SCADA set points, and we look at distributed energy resource coordination studies. A lot of times what we're seeing now is that when a company wants to install DER or a data center, that they have to coordinate with the local utility and sometimes install the protection in order to be able to connect to the grid so that they don't cause the outages and the damaged equipment that we're starting to see. Resonance and harmonic amplification. So inverters can introduce high frequency switching harmonics. And this in itself can cause the transformer windings to overheat. When we have resonance in circuits, that an example might be if you look at any kind of stringed instrument, musical instrument, a guitar, a harp, a piano, any kind of stringed instrument where it vibrates, the vibrations are different depending on the frequency that string is vibrating at. And so if you have electrical wire vibrating based on the electricity going in and out or on and off, then you can have a similar effect. And in a musical instrument, when we have a harmonic, we get an increase in the volume of the output of that instrument. And if that happens to an electrical circuit, we can cause damage. So we have to be careful about measuring, monitoring, and protecting against the harmonics. And what we do there is we can use filter banks, tuned reactors. We want to avoid resonant frequencies with inverter switching profile adjustment and harmonic impedance modeling during the interconnection study. So we look at it before we install it. We don't want to try and fix it after the fact. So what else is there? Fast frequency response. These batteries, they can come on in less than a cycle or a 1 second range. And, our grid protection may not be ready for that. We may have grid protection that's looking for a little bit longer trigger before we shut down whatever's causing the problem. So with this quick on-off ability of the batteries, we may end up inadvertently islanding or shutting in some of these BESS systems. So what do we need to do? We need to, determine what the BESS frequency, droop, and ramp rate limits are during that interconnection study, and make sure that we can, have ride through if it's safe for our equipment. So the key integration studies required are the load flow and contingency analysis, evaluate reverse flow impact, harmonic impedance scan, identify resonance risks, dynamic simulation, model BSS response to grid events, protection coordination study, validate inverter trip logic and reclosing schemes. And with that, I want to say thank you for the opportunity. I know it was quick. There was a lot of information. We've been talking for about 45 minutes. Now it's your turn. If you have any questions for me, just realize I'm a fire protection engineer who works for an insurance broker. I worked for power companies for 25 years, not as an electrical engineer. So if I can answer any of your questions, I would be happy to. And I'll turn it over to you guys if you have any questions.
Thank you, Mr. John. interesting topics today. And please, anyone have any question, just write it at that chatting box. While we are waiting for the questions, we are glad to announce to you our and invite you to attend our GCC Power 2025 in Kuwait this November, between 10th to 12th of November. And Mr. John and all the audience are invited to attend.
Thank you. And yes, I'll confirm that I'll send the presentation along, all the slides. So I should have said that earlier. You didn't have to take as detailed notes, but now maybe you have better notes. And I think I asked about, or I answered the question about hydrogen generation, CO generation, and fire hazards. And like I said, you either need to vent the gases, you need to, like I said, Tesla uses sparks to prevent the fire. They actually ignite the gas before it builds up to a point where it could be a bad explosion. That's their method. But honestly, I think before we even get to the point of generating it, that remote monitoring is going to be the solution. Having a system that either has AI built in on site or uses AI on the back end to analyze your battery health. You get weeks of protection before you even get into a point where you're going to make gas that you have to detect. So I do believe that that's a technology we all need to look at. And as far as modern fire protection room for lithium batteries, I encourage you to go watch one of my latest interviews. It's a dry ice system. And what they do is they use liquid nitrogen, 30% liquid nitrogen, and the rest is dry ice in the consistency of sand. And now when you freeze CO2 and make it into dry ice, it only really needs to be 100 below zero. But when it's in liquid nitrogen, it's like 300 below zero. It's very, very cold. And it turns into a slurry that can be discharged into a battery. And so many fire protection engineers think about the fire triangle, the heat, fuel, and oxygen. And they think about removing the fuel or removing the oxygen to put out the fire. But what this system does, it's called ELSA. And if any of you've seen the Disney movie, the Frozen, they called the movie, the queen in there, his name is Elsa, and she's the queen of ice. Basically, she can make ice anytime she wants. And that's what this system does, is it will inject extremely cold nitrogen and CO2. It doesn't leave any residue, but it stops thermal runaway by removing the heat portion of the triangle. So thermal runaway doesn't happen if the batteries are cold. In fact, when they do their full-scale testing, they destroy a battery to get it started, and they get the fire going, and then they hit it with the dry ice and liquid nitrogen, and quickly it arrests the thermal runaway. But then it gets so cold that in order to dispose of the battery, how do you dispose of a lithium ion battery that's already damaged, that you did a full scale test on, but it didn't propagate? So you've got a lot of fuel left in it, but it's damaged. Well, you light it back on fire. And how do you light a battery like that on fire after it's been frozen so bad and it's so cold? They take torches and they heat this battery back up because they have to thaw it out. So it's a very interesting technology. In the video that is on my YouTube channel and on LinkedIn, it shows them extinguishing a 500 square foot oil fire as well within seconds. They, the big problem with using AFFF foam is that, we have to worry about PFAS and what's the replacement for PFAS. Well, this dry ice system, ELSA, will replace that. And it can be used either in, chemical manufacturing, refineries, or in battery energy storage. So it's got a really bright future ahead. I encourage you to check it out. And there's links in that video to reach out to the manufacturer of the ELSA dry ice system. Can battery energy storage systems be utilized for AI data center applications and smooth power fluctuations? If so, what additional features or requirements should be specified for the BS? Yes, in fact, I said that Tesla's doing that here in the States at their in Memphis. They didn't have time to order enough solar and enough wind equipment to power the, the data center. So they're using simple cycle gas turbines, and they run the power to the BESS, and then from the BESS they go into the data center. As far as additional features or requirements on the BESS, I would think that actually, in this case, you're going to have to deal with cycling, the potential for the gas turbines to go up and down. So the supply of power to the BESS may not be as smooth as a grid source of power. And you would have to, again, consider what the cycles do. But it is being done. That is one of the potential applications, BESS and AI. What's the impact on system inertia of battery energy storage systems? I know very little about system inertia other than what when I was growing up in the utility industry as an engineer in the plants, we used to see a graphic that would tell us what our spinning reserve was. So we knew that all the steam turbines out there and the generators had lots of mass, and that injected lots of inertia into our grid. And that would help whenever there was, say, a steel mill near us that went down and all of a sudden the load dropped. Well, our big steam turbines would, balance the load. And as we've shut these down, we see that, the grid is more frail. It's more susceptible to drops in load or spikes in load. So batteries can help that. They are one of the technologies that are going to help improve system inertia after we have more of them. Since NFL UL 9540A doesn't define explicit pass-fail, how would you interpret a test result where a module exhibits internal cell-to-cell propagation, but there's no propagation at the container level? Would you still consider the overall design compliant or adequately mitigated? Now that's going to determine, by the authorities having jurisdiction, or what we call them in the United States, but the insurance company and is going to have to chime in on whether they're going to accept that result or not. And if you have, say, a high enough deductible, or the risk is yours, then that's up to you to accept whether cell to cell is adequate, or whether you need to also have it pass as far as module to module. But what you use the data for is to determine whether you're going to install a suppression system or just make the spacing larger. Let me also say that I'm working on another topic along with suppression systems. You know that in fire protection, if you put a water spray system or water mist system, that you could, not so much with water mist, but with water spray, you could have runoff. Or if you have firefighters that show up and start spraying water at a module, you could have contaminated runoff. And so there's some thoughts that we could install receiver tanks for each of the module or each of the containers. And what that would do is that if we had a fire, the runoff water would not contaminate the site. So it could be looked at as environmental protection, obviously, but it's also business interruption protection, because if you've got a site where you have environmental contamination after a fire, you may be required to shut down until you clean up all of that contamination. And if you have a container with a runoff tank that prevents the soil from becoming contaminated, then you actually have, increased your ability to restart the facility sooner. You don't have to shut down until all the decontamination is done, because all you have to do is pump out that storage tank. So that's another on the horizon technology that's out there. All right. So thank you for your response. Could you please clarify if such an application would have any impact on the lifetime of the battery energy storage system? the battery energy storage system lifetime is probably going to be driven by obviously it's technology, but the cycling, the heat up and the cool down. The if it is not cycled very often, it's going to last longer. But if we have to cycle it, then we're going to wear it. That's where most of the any electrical equipment wear comes from, is from cycling. I will point out that, people think that about gas turbines. And let me just throw a sidebar out there, since some of you guys also have gas turbines, that all cycling does in gas turbines is it moves the risk. So if you cycle up and down, the hot gas path will be le- affected more than, say, if you don't cycle. If you get up and get to a steady state and keep it running all the time, then you're not going to be heating up and cooling down that hot gas path, but you are going to be ingesting a lot more air. So the compressor end of the gas turbine is going to see more risk, because there's more risk of inducing foreign objects that could cause damage. So uh, just be aware that cycling is not bad in itself for gas turbines, because all it does is moves the risk either from the hot gas path or to the upstream compressor end. As far as battery energy storage system, cycling is going to be what causes the wear. Can BESS support a system black start? Yes, it can. In fact, that's what we have out in California, as I described. There's a site that's got 8 LMS 100 gas turbines, simple cycle gas turbines. They're there in the middle of the valley to support the grid when the wind turbines stop. And it can happen out in the Palm Desert. But what this system did was, in order to black start the facility, rather than using the traditional old diesel equipment, where we have a diesel generator, they installed a battery energy storage system. It's smaller than what you would see for grid support, because all it's got to do is start a couple of 100 megawatt gas turbines, which isn't as difficult as supporting the entire grid. But that's how it can be used. It probably, if it was large enough, it could, and it was designed for it, it could probably support black start. The only thing is that, the state of charge, is it going to be ready to go all the time? Whereas, in this case, the system that supports the gas turbines, that's all it's there for. So it's always fully charged. A system that is typically running the grid, shaving the peak, it's always interacting with the grid. It may not be, charged when it's time to support the black start. So, are there any other questions? I really appreciate the opportunity to do this, guys. It was fun. Any special settings required for black start? Again, like I said, the only things that I could see are that making sure that you have a minimum charge in the batteries, that you're always paying attention to having enough charge. If they're uh, supporting the grid and they're responding to an outage of another piece of equipment on the grid, they may be drained if that piece of equipment causes, a cascading chain reaction. So I think you have to be careful about, deploying the power from a black start system, and that all has to be taken into account when you design it and configure it to operate. Thanks for all these questions. These are great. I really enjoyed working with you guys, and love to do it again sometime. Thank you. I'll leave it to the GCC to determine if we're done and everybody can say goodbye. All right. Thank you all. Well, there's been another question about the AI monitoring services. Volitica and Electra are the two companies. And like I said, their complete interviews with their CEOs are available through my LinkedIn, which is on the very first page. Just go to my profile and you'll find them. But also, I can show you over here. Let me share real quick. And just for those who haven't been to my YouTube channel, there we go. This is what you'll find on my YouTube channel, but there's a video on the dry ice system. PV stop is very interesting. It's to extinguish solar module fires, but not just the fire, but to stop the power when the power when a module fails or a module has a crack or there's a fire in the building and you have to turn off the power. AI-driven control of work. So even in gas or in chemical manufacturing facilities, this AI control of work process is a very interesting one. This is Electra, the discussion I had where they use AI brains in the battery management system. Remote monitoring, this is the Volitica interview. Fire Rover is very interesting, but just, there are probably 50 or 60 videos that I've produced over the last couple of years, all on energy risk engineering. So enjoy those if you can. And the links to all that are on the first slide of our presentation today. So I'll let you go. We've been talking for about an hour and a half. Thanks again, and have a great day.
Yeah, hello, Mr. John. Thank you, and thank you for the audience. Now I have my one of our board members here need to comment for this webinar, Mr. Sani Al-Qusaybi.
Okay.
Hello.
Hello. Yes.
Yes, I'm with you. Thank you.
Thank you.
Thank you very much for your presentations. It's quite very good information we have received. I have a general question. What are the best modeling techniques you can use for system analysis when we do, whenever we model the system for example, voltage stabilities, for system stabilities. So what is the best models to be used for battery energy storage systems?
Well, I'm going to answer this question with a little inside information. In my job, whenever a question comes up that I can't answer, I go out and start doing the research and I'll write a white paper for you. And hopefully that, I'll get it done quickly, but I don't work with those models directly. Again, I help clients get insurance. So I deal with the insurance questions and the risk at a higher level. But you've given me a great idea for another topic that I will explore. I'll write a white paper on modeling for electrical stability.
Okay, that's fine. Thank you very much. Because, in our today's energy transitions and usage of renewables and all different type of resources, we need to have very good modeling techniques. And as well, we have to train our personnel or staff in order to be able to model the right way our systems. So this is why I'm asking that question. Thank you very much.
Thank you. It's a great question.
Okay, thank you, Mr. John. Thank you, all of you. And shortly we'll get notice about our future webinars as well. Thank you.
Okay, thank you.